Okay, we're going over the practice test for discrete stats. Just be sure you got your formula sheet and your calculator on you. First question, we got to verify whether or not this is a valid probability distribution. So yes, sum of probabilities equals 1, and all probabilities are positive. So you probably should actually check. So if we go 0.17 plus 0.25 plus 0.3 plus 0.15 plus 0.1 plus 0.03, yes, indeed, it does equal 1. So that's good. Next thing we need to do is find these values here. So you want to do these in your calculator. So just clear out any lists you might have in there. So there's 5 up to that, and the probabilities corresponding to those values. Okay, once you got all those in, you want to go calc and then hit the set button. Make sure this says list 2 here for a frequency list. Once you've done that, you can hit 1 bar and you'll get all your values. So that first one there is our mean. So the mean, E of x, is 1.85. The standard deviation of x is 1.31, go 3 significant figures. And the variance is the standard deviation squared. I might just make a little note of that. And we can roughly work out what that is. 1.31434 is the whole number. Well, not the whole thing, but a lot more decimal places. So we square that and get 1.73. Reason I've used more decimal places is some inaccuracies further down, like 3 or 4 decimal places in, when you square a number can blow up to bigger differences. So you want to use a few more decimal places. E of x plus 1. So E of x plus 1 is E of x plus 1. And E of x was 1.85. So that becomes 1.85 plus 1. So that's 2.85 there. And sigma 5 take x. So what you need to do, that's mod of minus 1 times sigma of x. So that's 1 times sigma of x. So in fact, that's just the original standard deviation, 1.31. So what you do is you throw out the 5 and the minus 1 that was with the x, we just do mod, so that becomes positive 1. Okay, 74% of population enjoy TikTok apparently, and we want to find the probability that all of them enjoy TikTok. So let x be the number of people in a sample of 15 who enjoy TikTok. Then we need to say that x is distributed binomially, and this is, let's see, 15, and the probability is 0.74, and we'd like to know the probability that all of them enjoy it, so the probability that x is 15. Okay, so we can just do this directly with binomial distributions. So if we go there, dist binom PDF, 15, 15, and 0.74. We execute that and we get 0.011. 3 significant figures, I guess, should be 109 technically. Cool. Exactly 10, so probability that x is 10. Now that you've already done the notation for the first bit, you don't need to redo it. So we can just exit out here and we're going to go 10. And we can execute that, figure out what it is, 0.176. And less than 12. So what we want to do is exit out. We want to go binomial CDF. Lower can be 0, upper can be 11 because it's strictly less than 12. You don't include 12. So probability that x is less than 12, I'll make a note. This is equal to the probability that x is less than or equal to 11, which roughly equals 0.574. Between 6 and 8 people, including 6 and 8. So here's where you would set your lower to 6 and your upper to 8. And we'll execute that, 0.0673. And the probability notation would be 6 is less than x is less than 8, including those two numbers. And calculate the expected number of people. So the expected value of x is NP. N was 15 and P was, I think, 0.74. So 15 times 0.74. And that's something that we can just directly work out on the calculator to get 11.1. And next we need the standard deviation. So the standard deviation, we get a formula with binomials, NP, 1 take P. Now I think these formulas may even be on your formula sheet. Let's just verify that. All right, so we can sort of see on there, yes, they are. So right there, NP and NP1 take P. So that's good news. Okay, moving on. Well, actually, we need to calculate that, don't we? So this is root of 15 times 0.74 times 1 take 0.74. And we can work out what that is. So let's see. Yeah, 1.69 or 1.70. We round it up. And people. Excellent. Decide whether these are Bernoulli variables. So you roll a single die. So yes, 2 outcomes, 0 and 1, and P is 1 out of 6. No, more than 2 outcomes. So we could have X is 0, 1, 2, or 3. So this is actually binomial, this one. Okay, suppose it does represent a Bernoulli variable. So we got 0.25 there for our p-value. That means the other number must be 0.75. And we want to state the mean of x. So the mean of x is, sometimes you use the mu symbol, but it's p, which is 0.25. And the standard deviation, this is p1 take p under a square root. So it's actually the same formula as a binomial. You only have n equals 1 in a Bernoulli distribution. And they also tell you this here as well. So that's very helpful. So it's 0.25 and 1 take 0.25, which roughly equals, and then we can work out what that is. Root 3 over 4, but probably more sensibly 0.433. Beautiful. All right, now we need to look at S5. So the expected value of S5, this is 5 times the expected value of X. That's how S5 works. So this is 5 times 0.25. So this is 1.25 there. And then the standard deviation of S5, this is root 5 times the standard deviation of X. So this is root 5 times 0.433, roughly. Which roughly equals, I'm just going to times my answer by root 5 there, root 15 over 4, or 0.968. Okay, so that's how we get those ones. Now, what happens if I take a Bernoulli distribution and do it 5 times? I get a binomial distribution. N is 5, P is 0.75. We got 5 trials with the same probability. I've repeated, and I'm going to use the word independent. It's a binomial distribution. Cool. That's what you get when you stack a Bernoulli on top of itself. Okay, so moving on, we've got this situation here. Explain why x is a discrete random variable, because x can only take on whole number values. That's why. So that it doesn't have to only be whole numbers for it to be discrete, but if it is whole numbers, you know automatically it is discrete. So I'm going to go like finite number of possibilities in a given range. That would be more like a formal definition of discrete. Like if you cut off your range between 2 numbers, you'll only find a finite number of possibilities in there. Whereas if you're measuring heights, anything between like 190 and 210 centimeters, there would be infinitely many possibilities there. That's continuous. State all possible values of x. So how many are you taking? 2. So 0, 1, or 2. Construct a probability table. So what we've got to do here, 5 red, 7 blue. X is the number of blue, so we're going to have blue and red, and blue and red, and blue and red, and then we got to go, there are 5 out of 12, no, 7 out of 12 to get a blue, and there are 5 out of 12 to get a red. And then we've used a blue, so there's now 6 out of 11. Red, so it'd still be 5, so 5 out of 11. If we go down the red path here, though, we've used a red, so there's only going to be 4 out of 11 there. And then the other one must be 7 out of 11, because there's still 7 blues. X is the number of blues, and we want the probability out of that. So on this top branch, you've got 2, and then 1, and then 1, and then none. And they correspond to each branch there. Now the probability here is 7/12 times 6/11. and we can work that out. So if we do that, just on a calculator, we're going to get 7 out of 22. Similarly here, 7/12 times 5 out of 11. So we can just go and modify this. Okay, 35 out of 132. This one should be the same, 35 out of 132. But if you want to verify it, it's 5/12 times 7/11. You can check that. It does give you the same thing. And then 0 will be 5/12 and 4/11. So if we can work out what that is, 5/12 times 4 out of 11 gives us 5 out of 33. Okay, so now we need to make our probability table. So it's going to be x, and probability big X equals little x. X could be 0, 1, or 2. The probabilities for 0 and 2 are quite straightforward because you just read them straight off the table. And for this one, 35 out of 132. 35 out of 132. And I want to double that. I'm going to get 35 out of 66. Okay. So that one there is just 2 times 35 out of 132 because there were 2 lots of the ones there. That's why we got 2 of those. Everything else was just 1. Okay, let's double check that our thing is actually a PDF. And it would help if I actually wrote 33 there. And yes, that equals 1, so it's PDF. That's good news. Okay, find the expected number. So we can just go straight into our calculator here. Delete out any old lists you may have had. And we're going to go 012, 5 out of 33, 35 out of 66, 7 out of 22. Calc set, make sure you got list 2 as your frequency. List 1 bar 1.16 is the mean. So expected value of x roughly equals 1.17 if we round it up. And the standard deviation of x roughly equals 0.665. So you're just reading off that sigma number there. Okay, question 6, 120 households, and we found that 91 of them had a Netflix subscription. P hat is 91 out of 120. We can work out what that is. So let's have a look. 91 out of 120, 0.758, roughly 0.758. Then we want to calculate a 95% confidence interval. So we're going to go into stats and inter for interval. 1 prop, 95, x was 91, n was 120. Execute that, and we see we got 0.682. Less than p, and that's less than 0.835. Cool. So between 68 and 83% of YL households would have a Netflix subscription. That's what we sort of see there. Then we're looking at Stan subscriptions, and we've got this confidence interval. And they can include that Netflix, there's more Netflix than Stan. This is not supported. So their claim is not justified at the 95% level, as the 2 confidence intervals overlap. It is possible that P for Stan is either smaller or larger than P for Netflix. Something like that. So it's could be possible that their claim is true. So like, since we can't say for sure it's, what are they actually claiming? More Netflix. Since we can't say for sure Netflix is larger, we cannot support the claim. Cool. Something like that. Okay. And just to draw a little picture. So if you've got your 2 confidence intervals, you've got sort of 68 to 83 for the Netflix. So 0.68 all the way up to 0.83. And this is for the Netflix one. And then for the Stan, you've got 58. So up to 70. So 0.7 and 0.58. And you can see that this region here is the crossover. So it could be possible that you have Netflix down there and Stan up there. Or you could have them the other way around, so we just can't make that conclusion. Calculate the sample proportion, so P Stan. So what you need to do is take the average of the upper and the lower bound of the confidence interval. So this would be 0.701 plus 0.589 all over 2. And this roughly equals a number that we can work out. 0.645. Gravy. All right. Well, that's good. So based on the confidence interval, it's claimed that over 58% have a Stan subscription. Normally it would look justified based on the confidence interval as the entire CI lies above 0.58, so it looked justified at the 95% level. But they are making a claim about all Australian households, and the sample of just Whyalla households may be biased and not properly represent the population. Yeah, so something like that. You acknowledge that you would normally say yes just purely on the mathematics of it, but they've got a biased sample. So their claim might be a bit nicer if they said over 58% of Whyalla households have a Netflix subscription. Then I would be happier. But they can't talk about all of Australia if they've only surveyed one town. Especially like you've got differences with like country towns versus city towns, for example, as to like how much Netflix they may want to watch, and like many other factors causing those differences within different towns, not to mention differences between states. Okay, survey group wants to estimate people who like maths and they want a confidence interval with that width, calculate the number of people. So we do have a formula for this. This is 2 times 1.96 over WE squared, P star, 1 take P star. That's the formula. And we are going to use P star is 0.5 because we have no previous values of P hat. Okay, so this is going to be 2 times 1.96 all over 0.05 squared times 0.5 and 1 take 0.5. And we can just whack that all into a calculator and see what we get. I want to stress that that 1.96 number is only there because it's a 95% confidence interval. If it was a different confidence width, you'd have to work it out using inverse normal. So just be aware that can come up. So 1536.64, and you always round up. So we need 1537 people. Okay, so they do the survey with 1540. And they get that 1213 liked maths. So we can actually see how that compares to what we predicted the width would be. So with stats inter Z1 prop, we got 1213 and we got 1540, and we execute that 0.767. Less than P is less than 0.808. Okay. Now, one thing that I want to point out is if you look at that, we'll do it in a second, part D. First of all, we got the claim over 70%. Is this claim justified? You can say, yes, the claim is justified at the 95% level as the entire confidence interval lies over 0.7. And here we can actually say the claim is justified because they just surveyed Australians. They didn't survey like a particular group within Australia that may be biased. Okay, calculate the width of your confidence interval. So width is 0.808 minus 0.767, and that roughly equals, let's find out, 0.041. Groovy, all right. Explain why this width doesn't match your desired width of 0.05. So basically, if P with the hat over the top, can't type that, equals 0.5, then we'd get a width almost exactly 0.05. This is the worst case scenario, and this is the biggest n value we might need. So that's the start of it, the worst case scenario, biggest n value we might need. Since p hat, did we work out p hat? I don't think we did, but we can just go back to our interval and it tells you what it was anyway. You can do 1213 divided by 1540, but p hat was 0.787. Ended up being 0.788. We didn't actually need that many people to get the desired width. Hence, the width was smaller than initially expected, but we didn't know this until we actually did the survey. Something like that. Yeah, with these questions, I recommend you leave them till the end and you come back and add more elaboration just as you get more time. Okay, we've got the dice rolls here, and you've got to think about, like, for example, how do I roll a 9? Well, actually, how do I roll an 8? So I could get a 2 and a 6, I could get a 3 and a 5, a 4 and a 4, a 5 and a 3, and a 6 and a 2. So that was 5 ways, and that's how I've got the 5 in the table. How do I roll a 9? So I could get a 3 and a 6, a 4 and a 5, a 5 and a 4, and a 6 and a 3. So it looks like there are 4 ways to do that, and then the table sort of repeats back on itself like that. If we want to go for these numbers, we're going and dividing by 36. That's the total number of ways there. So for example, 1 out of 36 is that number that I put in the table there. So make sure you actually like verify the numbers in this table, how I got them, because then you'll know that you got it right. So 0.1111 would be that one there. Now I'm going to be extra cheeky and actually save myself a whole bunch of time. Don't want emojis on my calculator, calm down. All right, and then we're just going to delete out these probabilities. So I'm actually going to enter 1 out of 36 in that column. There we go. 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, and then we go back. So 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. And conveniently, I can just scroll up and down this to find the values that I actually want. So 0.1389 would be the next value if I round that. 0.1667, 0.1389, and then we can see that it sort of falls back down. So 0833, 0556, 0278. Okay. Check the table as a valid PDF showing you're working. So all probs add to 1. So we can actually do this. So 1 out of 36 plus 2 out of 36 plus 3 out of 36 plus 4 out of 36 plus 5 out of 36 plus 6 out of 36 plus 5 out of 36 plus 4 out of 36 plus 3 out of 36 plus 2 out of 36 plus 1 out of 36 equals 1. Trust me, it does. And all probabilities are positive, which is true. Now, usually I wouldn't write out that whole sum, but since it said show your working, we just got to be careful. So probability that 5 is less than x is less than 8. This is going to be all those individual probabilities added up. So between 5 and 8, so that's 0.1111 plus 0.1389 plus 0.1667 plus 0.1389. And I'm actually going to use the full fraction versions of those. So the 0.1111, this was 4 out of 36, 5 out of 36, 6 out of 36, and 5 out of 36. And we can work out what that is. So let's just chuck that into a calculator. Well, 4 plus 5 plus 6 plus 5 is 20. So 20 out of 36 should be our answer there. 0.5556 when we round it up. Calculate. Now this is why I put it in my list before, because now that I've got it in here, I can just go calc 1 bar, and x bar is 7. And the standard deviation is 2.42. Okay, now we got some funky questions here about normal distributions. So assume x is distributed normally with the mean and standard deviation we just figured out just before. So I might make a note. So from then probability that 4.5 is less than x. The reason you need the extra rounding is because when your calculator does a normal distribution, it doesn't know you're talking about whole numbers. So you just need to include the 0.5 either side, because that anything bigger than 4.5 would round up to 5 in that range. So we're going to go normal CDF. So yeah, any numbers between 4.5 and 5 would round up to 5. And any numbers between 8 and 8.5 would round down to 8. So 2.42 is that, and the mean is 7. Technically, I should use the full standard deviation. But you get about 0.5815. 0.582. I'm actually just, otherwise that'll bother me that I've done it. Let's go back in and use the full standard deviation and see if that makes a difference at all. 2.4152294. 945. We'll see if that makes any difference. No, it didn't, but you can see it almost did. Like it almost would have rounded up to 58.3%. So these ones here, so you've got actual value 0.5556, and then our guess with the normal distribution is 0.582. So these values were close, but a little bit off. Based on the central limit theorem, we need NP is greater than 5 and N1 take P is greater than 5 to be approximately normal. We don't. Well, this is for P hat. It's a bit tricky here, actually. I might get rid of that bit. That's usually true with the NP and the N1 take P, but the P value here is a little bit hard to define properly, so I might just leave that bit there. A bigger N value would mean this is closer to a normal distribution. I'm just going to say by the central limit theorem, but I'm not going to give too much about the specifics of N and P. But if there are 50 dice rolled, so this might not be 100% perfect, but would be a lot better as the N value is much larger by the central limit theorem. So basically what the central limit theorem tells you is you take more samples of dice. Actually, no, I know what the mass is. It's sort of like SN. So I think when we looked at SN, we had particular constraints on N. And I reckon it was N greater than 30 was your rough guide. So like your rule of thumb. So that rule of thumb would fail there and it would win there. If you're talking about binomial distributions or like P hat values, then you would expect the NP and the N1 take P thing. Anyway, we'll use normal distributions to get this. So expected value of y is, well, y is S25. So if we roll 2 dice 25 times, that equals rolling 50. So expected value of y is 25 times the expected value of x. And let's see, that was 7. So that's 25 times 7. And we can work out what that is. So about 175. And the standard deviation of y is root 25 times the standard deviation of x. So that would be 5 times, let's see, 2.42 roughly equals. So let's go. Yeah, I should probably use the full version, but we'll just go with 12.1 for now. Therefore, assume y is distributed normally 175 and 12.1. The probability that 139.5 is less than y is less than 160.5. So you got to add on those 0.5s either side is roughly equal to. And we can work that out just using normal distributions. So if we go dist norm NCD, 139.5, 160.5, 12.1 and 175, then we should get 0.113 or 0.114 once we round it up. Wonderful, good stuff. Okay, so y would be better. Now, one optional or you could have done is x is 1 dice and y would be S50. So just for example, if you wanted to do that, your stats menu, you would have to work out all the mean and standard deviation for 1 dice. So if we get rid of all this, when I roll 1 dice, it looks like that. And each of those probabilities is 1 out of 6. And then if I calculate my mean, it's 3.5. So mean is 50 times 3.5. And the standard deviation is root 50 times 1.71. And if you work out what those numbers are, so 50 times 3.5 was 175, that's the same mean we got there. And root 50 times the standard deviation for 1 dice, 1.71, should give you the 12.1 value that we got before. So that's another way that you could do that question there.